Hello, this is Philip Myers of PEMY Consulting. Welcome to Strength of Materials for Tank Engineers Part 12. We are at the point where we can now talk about normal and shear stresses in pressure vessels. This is a cylindrical pressure vessel. The biaxial stresses acting on the shell are sigma A, or the axial stress, and sigma H, or the hoop stress. Can you guess which one is larger? The formulas on the right are for the thin wall pressure formulas we reviewed earlier. They give the axial and hoop stresses, which are principal stresses in the pressure vessel. Note that the hoop stress is twice as large as the axial stress. Consider the stress element on the shell of the pressure vessel as shown. Let's define the coordinate system with the x, y, z triad. We'll make the x-axis in the axial direction, the y-axis around the girth, and the z-axis will be normal to the surface of the cylinder. Along these axes, we therefore have sigma x, called the axial stress, and sigma y in the circumferential direction, which is a hoop stress, and the radial stress in the z direction, or normal to the surface, which we are assuming to be 0, and which we designate as sigma z. The axial and hoop stresses are principal stresses, so we know that in these directions there are no shearing stresses. Sigma z is 0, but it is still a principal stress. And along the 45-degree line, the shear stress tau AH has a maximum value. Let's construct the Morse circle for the two principal stresses acting in the shell, the hoop and axial stresses. Sigma H is the largest principal stress and is so plotted at the extreme right. Sigma A is the other principal stress in the XY plane and must be plotted at the left. At the center of the Morse circle is located at the average of the principal stresses and is 3 PR over 4T on the principal stress axis. The radius of the Morse circle gives the maximum in-plane shear stress tau xy, as was shown in the previous slide. Now consider the outside surface of a pressure vessel where the radial stress is 0. The red Morse circle is what we just did based on the hoop and axial stresses, which is in the xy in-plane stress state. But now we consider the z, or radial direction. Because of z, there are two additional Morse circles for the rotations about the y and x axes. The two Morse circles are shown in black. The largest one is for the rotation about the y-axis. The largest shear stress is given by the radius with the red arrow, showing its magnitude. In this case, the absolute maximum shearing stress is PR over 2T, since it is half of the sigma y value, which is the hoop stress. But here we have looked at the outside surface of the pressure vessel where the radial stress is 0. We'll next look at the inside surface. The internal pressure of magnitude P on the shell produces a radial stress in the z direction. The effect is shown by the red dot on the left side of the large Morse circle. The outside surface Morse circle is shown by the light gray smaller circles with a left boundary on 0. So the absolute maximum shearing stress is out of plane at 45 degrees to the YZ axis. This shows that if the material shearing stress failure were to occur, it would be on the inside surface at 45 degrees. Recall that the spherical pressure vessel has equal normal stresses in all directions by symmetry. Recall that the stress element has no shear stress, and the stress in both directions is an equal biaxial stress condition with the magnitude of PR over 2T. So what would a spherical pressure vessel look like in terms of a Morse circle? Consider a stress element on the outside surface of a sphere wall with both normal stresses being principal stresses in any orientation of the stress element on the surface, which means that every direction is a principal stress direction and there are no shear stresses in plane, that is in the XY plane. The Morse circle has a degenerate radius of 0, so it is just this, a point, which has a value of PR over 2T as previously shown. But even though the in-plane shear stress is 0, the absolute maximum shearing stress is not 0, as we'll see. The Morse circle for the absolute shear stress on the outside of the vessel wall is shown by the blue circle. But because there is an internal pressure, we must look at a small stress element located on the inside wall of the pressure vessel. As shown earlier, the stress in the z direction is negative p, and when this point is plotted on the principal stress axis, we get a Morse circle indicated by the larger red circle. This represents the absolute maximum out-of-plane shear stress for the spherical pressure vessel and is given by this equation. This concludes our discussion of stresses in pressure vessel. We next move into failure theories applicable to steel pressure equipment. Thank you.